We can start. Our last speaker of the morning session is Lajos Molnar from University of Szeged, and he's going to talk about transformational structures and positive definite cones in C-star algebras. Lajos, please.
Thank you. First of all, I'm also grateful to the organizers, especially to Javad, for the kind invitation. It's really a pleasure, big pleasure and an honor for me to speak at this institute, the Fields Institute, and in this program. I will speak about transformations of some structures on positive definite cones in C-star algebras. And if those algebras are commutative, then they are algebras of continuous functions and compact houses of spaces. So one can say that our transformations are operators on function structures. But to tell the truth, concerning those investigations, the really exciting case when those algebras are non-commutative. Okay, so I will give a survey of our recent work on different symmetries of algebraic and geometric structures on positive definite cones in C-star algebras, and we will present precise descriptions of various algebraic isomorphisms, mean preservers, surjective isometries, and so on. The plan of the talk is the following. First, I will survey what we know about Jordan star isomorphisms of C-star algebras, and then I will present results on certain algebraic isomorphisms of positive definite cones, then mean preservers, after that isometries and generalized isometries, and in the last part I will speak about preservers of norms of means. So as you will see, our key concept here is that of the Jordan star isomorphisms. If we have two C-star algebras, then a bijective linear map J from A to B is called a Jordan star isomorphism, also called C-star isomorphism, if it respects the square operation, or equivalently, it preserves the so-called Jordan product, and also respects the involution, the star operation. Those isomorphisms are the most fundamental symmetries in C-star algebras. They have several applications in various areas, and there are several important properties, several important preserver properties what they have. Here is a list of them. So if we have a Jordan star isomorphism, then it is necessarily a surjective linear isometry. This is necessary in order isomorphism. It preserves the order, the usual order in both directions. It preserves commutativity in both directions. It preserves projections in both directions, also unitary elements in both directions. And also it preserves invertibility in both directions. More precisely, it respects also the inverse operation. It follows that such a map necessarily preserves the spectrum of elements, and then one can easily prove that any such isomorphism respects or compatible with the continuous functional calculus in this way. And so on. There are several such properties, and it turns out there are several results in the literature which say that in many cases the above preserver properties more or less characterize Jordan star isomorphisms within the collection of linear transformations. And the results that I'm going to present can also be viewed as characterizations of Jordan star isomorphisms, but there is a main difference here, namely in the following results, we do not assume any kind of linearity. And we will see that our transformations are still quite closely related to Jordan star isomorphisms. Okay, So our domain and codomain will be positive definite cones. And why? Because there are various structures on positive definite matrices which appear in different areas of mathematics, engineering, and other areas. For example, engineering, optimization, quantum information science, machine learning, and so on. Here our main interest is in various algebraic and geometric structures on positive definite cones, but not in the simple setting of matrices, but in the more general setting of C-star algebras. And we will describe the corresponding nonlinear automorphisms, isomorphisms, or in general, one can say symmetries. As I said before, we will see that in many cases, those transformations are closely related to linear Jordan star isomorphisms between the underlying full algebras. Some notation in what follows. When we speak about C-star algebras, we always mean unital C-star algebras. And so if A is such an algebra, then A sub S denotes the space of all self-adjoint elements of A. A plus is the positive semi-definite cone consisting of all positive, or in another terminology, positive semi-definite elements. And A plus plus is the positive definite cone, which is a set of all positive invertible elements. So first, let's consider algebraic structures on the positive definite cone. So operations. The most natural operation, or the first operation what comes to one's mind, is the addition. So what about the additive structure? This is an easy thing. I mean, relatively easy thing. That the corresponding isomorphisms, that means bijective additive maps between positive definite cones in C-star algebras, can be completely described. Namely, they are Jordan star isomorphisms between the underlying full algebras, composed by two-sided multiplications with elements from the positive definite cone of B. It's obvious that every such transformation is an additive map. What is interesting that the converse is also true. So any such any additive bijection is of that form, meaning that if it is on an additive map, it has more algebraic features. It's more or less, to some extent, it preserves also the multiplicative structure, at least the Jordan structure. I mean, modulo this two-sided multiplication. The next is the multiplicative structure. This is more exciting because the usual product is not an operation on the positive definite cone. So we need to consider some other notion of or concept of product, and this is what we consider here, and we need to consider here. You will see why. You will see later. This is the Jordan triple product, ABA. This is an important product in ring theory, for example. And not only that, also AB inverse A, what we call inverted Jordan triple product. And the corresponding morphisms, corresponding bijective maps preserving those products are respectively the Jordan triple isomorphisms when the operation is the Jordan triple product, and inverted Jordan triple isomorphisms when the product is the inverted Jordan triple product. One more, so I would like to emphasize once more that here no linearity, not any form of linearity is assumed. What is the correspondence between those two kinds of transformations? One can easily see that every Jordan triple isomorphism is necessarily an inverted Jordan triple isomorphism, and there is a way back. So if we have a Jordan triple isomorphism, then this new transformation, so if we compose this by this two-sided multiplication, then we obtain a Jordan triple isomorphism. So one can say that the studies of them are equivalent. Okay, They are very closely related. Okay, and what about the structure of Jordan triple isomorphisms between positive definite cones? Unfortunately, I do not have a result in the general setting of C-star algebras, and you will see why. I can give a result only for von Neumann algebras, more precisely only for von Neumann factors. And I need a concept, a notion, namely we call a linear functional tracial, if it behaves like the trace. So LAB is L of BA for every A and B. And we know that on finite von Neumann factors, there is a unique normalized tracial positive linear functional, which is usually called trace, and this is denoted by trace, the usual way. And then the result is the following. If we have two von Neumann algebras and one of them is a factor, that means its center is trivial and not of type 1, 2, this will be important. Then any continuous Jordan triple isomorphism between the corresponding positive definite cone can be described. We have two cases, when A is of infinite type and when A is of finite type. The simplest case is when A is of infinite type. In that case, there is either an algebra star isomorphism and an algebra star anti-isomorphism, and a number C plus minus 1, such that phi is of this form. So it's either an algebra star isomorphism or algebra star anti-isomorphism, may be composed by the inverse operation. If A is of finite type, then some additional thing shows up. If you think of matrix algebras, you know that there is a functional, namely the determinant, which is multiplicative. And that's the reason that here the situation is a little bit more complicated. So we still have this part as above, but there is a functional which multiplies this part, namely this is you see exponential of d times trace log a. It's a kind of power of determinant. Okay, and this is a precise result in the sense that the converse statements are also true. So we have the complete description of Jordan triple isomorphisms between positive definite cones in von Neumann factors, which are not of type 1, 2. What happens if they are of type 1, 2? That means that it's the matrix algebra of 2 by 2 matrices. Quite surprisingly, the proof in that case was really difficult. This is joint work with Daniel Virostek. And actually in that paper, we described not only the isomorphisms, also the endomorphisms. And the conclusion in the case of isomorphisms is just the same as before. And interestingly, we also found some application, namely namely the structure. We could describe the structure of the continuous automorphisms, actually not only automorphisms, but even endomorphisms of the operation of the Einstein velocity addition, which is the most fundamental operation in the special theory of relativity. So it has such an application. Of course, one can immediately put the question that what about the case of C-star algebras? I mean, in the previous results. So here A and B were von Neumann algebras. I don't know. I have no idea. I don't know the answer even for von Neumann algebras, which are not factors. Open question. Okay, let's move further and consider means. Means are important operations on positive definite cones, and there is a huge, quite big collection of means, which are called Kubo-Ando means. I don't go into the details, I just give the definition in the setting of C-star algebras. So if we have a operator monotone function on a positive half line, which is normalized by this condition, then the corresponding Kubo-Ando mean sigma on the positive definite cone of A is defined in this way. And the most important properties of those means are the monotonicity in their variables, monotonicity with respect to the usual order, and also the transfer equality or property, which means the invariance under all congruence transformations. So this operation is invariant under all congruence transformation, under all two-sided multiplications with positive invertible elements. And naturally, the most distinguished Kubo-Ando means are the arithmetic mean. It corresponds to this operator monotone function, the harmonic mean corresponding to this function, and the geometric mean corresponding to the square root function. And in that case, we obtain the arithmetic mean, no surprise, the harmonic mean, no surprise, and the geometric mean. And this is a little bit complicated. So as an operation, it is not, yeah, so it's rather complicated. And there is a geometric background behind this geometric mean. I mean that on matrix algebras, there is a certain Riemannian geometry in which the midpoint of the geodesic connecting A and B is exactly their geometric mean. So one can say that geometric mean is a kind of geodesic midpoint, and then one can consider means in general, at least symmetric means, as kinds of midpoints. And then mean preservers can be viewed as kinds of midpoint preservers. And I don't have results concerning all means, but we have a certain collection of means concerning which we have some results. Those are the power means. Power means form a parametric family connecting all those three fundamental means. So if we have a P between -1 and 1, and P is not 0, then we consider this operator monotone function and the corresponding Kubo-Ando mean with what is called the power mean, Kubo-Ando power mean. And if here P tends to 0, then as a limit case, we obtain the geometric mean. So when P is -1, we have the harmonic mean. When P is 0, we have the geometric mean. And when P is 1, we have the arithmetic mean. And what are the isomorphisms corresponding to those power means? If P is non-zero, then the structure is simple. The structure is the same as what we have seen before concerning additive maps. Here we need to assume continuity. So if we have a bijective map between the positive definite cones of C-star algebras, which preserves any of those means, then we can describe the precise structure. Such a map, those maps phi are exactly the maps of the following form: a Jordan star isomorphism composed by a two-sided multiplication. Once again, this is easy to see that any such map preserves those means, but the converse is not very easy to prove. And actually, the proof is based on a structural result concerning the following type of maps between positive definite cones, namely positive homogeneous order isomorphisms. And we obtained the structure, the description of those maps as a consequence of our result concerning Thomson isometries of positive definite cones. I will speak about the details later. So the proof of this depends on something quite different, a quite different result. What about the geometric mean? Because here P was not 0. So we have the structure in that case when P is not 0. When P is 0, then we have the geometric mean. What about the geometric mean? The story is a little bit different, but will be familiar. Why? Because there is a famous result due to Anderson and Trapp that the geometric mean can be characterized as the unique solution of this equation. And although the geometric mean as an operation is quite complicated, what you see here on the left-hand side is as an operation is not so complicated. This is exactly the inverted Jordan product, Jordan triple product, what I mentioned before. So one can see that maps which preserve the geometric mean are exactly the maps which preserve the inverted Jordan triple product. And then we know that inverted Jordan triple isomorphisms are closely related to Jordan triple isomorphisms. The difference only the appearance of that two-sided multiplication. And we know the complete structure of Jordan triple isomorphisms, at least for von Neumann factors. Putting together those things, we obtain the following. So if we have von Neumann algebras, A is a factor, we have a continuous bijective map between the positive definite cones, which preserves the geometric mean, then we obtain quite the same as before concerning Jordan triple isomorphisms. The only difference is the appearance of those two-sided multiplications. In both cases, when A is of infinite type, or in the case when A is of finite type. And also here, the converse statements are also true. So this is a complete characterization. The natural question arises, what about, so we have the structure for a certain parametric family of means. This is a thin set in the set of all means. So what about general Kubo-Ando means? Oh, I have absolutely no idea. That's a difficult problem. I even don't know how to attack that problem in that general setting. So an open problem again. And one can also consider not necessarily bijective maps, so not necessarily isomorphisms, but endomorphisms. And if one wants to treat them, then the most simple case when the codomain is the most simple C-star algebra, the one-dimensional C-star algebra. So when we have so-called functionals of means. So when the codomain is the positive half line. What about those power means? If we consider the arithmetic mean, oh, that's very easy, because any non-zero positive linear functional f restricted to the positive definite cone is a functional of the arithmetic mean. It preserves the arithmetic mean. The same holds for the harmonic mean. A little bit change the map in such an easy way, and we obtain functionals of the harmonic mean. What happens when p is 0? What about the functionals of the geometric mean? You remember that I mentioned that for matrices, the determinant is a functional of the Jordan triple product. It's also functional of the geometric mean. And more or less, this is true for any von Neumann algebra. Namely, if we have a continuous function which satisfies this identity, so it's a functional of the geometric mean, then, and actually this is an if and only if statement, then we have a tracial bounded linear functional L, which is real valued on the self-adjoint elements, and a positive real number such that f is of this form. So once again, it's a kind of determinant or power of determinant multiplied by any positive real number. This is once again a precise description. What about the other power means? the following interesting thing happens concerning the other Kubando power means. There are not constant functionals. At least if we assume that the von Neumann algebra is not of it does not have type 1,2 or type 1,1 direct summand. In that case, if it's a functional of any other power mean, then it is necessarily constant. This is a nice thing, because in that case, we can characterize the three fundamental means among the power means. But what about the other means? So is this a characterization? Is this a possibility to characterize those three fundamental means in the collection of all symmetric Kuban domains? I don't know. I don't know even for matrix algebras, but I think that this is an interesting question. So once again, an open problem. And now Thomson metric and Thomson isometries. This is one of the most important metrics on the, I would say the most important metric on the positive definite cone of a C-star algebra. What is the definition? Here is the definition. You see that this quantity, this quantity involves the order and also scalar multiplication. It's easy to see that one can write a formula, a more explicit formula for this metric. This is it. And in fact, it's again a kind of, so there is a differential geometric background here, namely it's a shortest path distance in an appropriate Finsler type geometry on the positive definite cone. And this has a number of applications. I mean, this metric has a number of applications. Its key property, it's the property which strictly distinguishes this metric is that it makes the positive definite cone a complete metric space, while its topology is the same as the topology of the C-star norm. And in the C-star norm topology, the positive definite cone is an open set. But in this metric, this is a complete metric space. So because of that, there are several applications of this metric in various areas. And of course, it's a natural question that what are the corresponding isometries? What is the isometric group of this metric? And one can easily see that if you consider Jordan star isomorphisms, of course, restricted to the positive definite cone, the inverse operation and two-sided multiplications, they are all Thomson isometries. For example, the two-sided multiplication is a Thomson isometry because of this, because it respects the order and also respects scalar multiplication. So what is the structure? What is the complete structure? And it turns out that more or less what I have listed here, those three types of maps, they are the generators of that isometric group. This is true to some extent. So the result is the following. This is joint result with my Japanese friend, Osamu Hattori. So a surjective map between positive definite cones is a Thomson isometry if and only if, once again, a precise description, we have a central projection in B and the Jordan star isomorphism between the underlying algebras such that phi is of this form. So we have this two-sided multiplication, and what is inside, it's a kind of direct sum of a Jordan star isomorphism and the Jordan star isomorphism composed by the inverse operation. So that's it, and I don't have time to go into the proofs and not even to mention the fundamental steps of the proof, but maybe 2 or 3 sentences. Following the main ideas this is not a proper expression follow, because the argument needs several adjustments, but still somehow in some sense following the ideas behind the proof of the famous Moser-Ulam theorem, saying that the surjective isometries between non-spaces necessarily preserve the arithmetic mean. They are affine maps. So somehow one can show that something similar is true for the Thomson isometries. The difference is that the Thomson isometry preserves not the harmonic mean, not the arithmetic mean, but the geometric mean. That's a very nice fact. I was very happy when I found it. And then if it preserves the geometric mean, we have a structure. We have a structural result for such maps. The problem is that we have that structural result in the setting of von Neumann algebras, not for general C-star algebras. But don't forget that our map here also an isometry, and because of that we can do something. So we can prove that result using, for example, so there are such ingredients that the user Reed-Rother formula, and also the famous result by Cadison describing the surjective linear isometries between C-star algebras, but linear. So we have to go somehow to linearity, and that's the point, the main point. Okay, so there is a very useful corollary of this result, what we call the corollary. This is our big corollary. It says the following: if we have C-star algebras and positive definite cones, and if we have an order isomorphism between them, so a map which preserves the order, and positive homogeneous, so respects positive scalar multiplication. In that case, we have the complete structure of that map. Namely, once again, this is a Jordan star isomorphism composed by a two-sided multiplication. So if it is order isomorphism plus it's positive homogeneous, then it is automatically additive. Okay, so how we can get this corollary from the previous result? Very easy, because this part cannot show up, because this part is not homogeneous. Okay, so this part disappears, and what we obtain is that P is necessarily 1, and we are done. That's all. But this consequence, this corollary is very, very useful. And one more thing: if we drop the positive homogeneity, then the result is no longer true. Why? Because in the simplest case of one-dimensional algebras, that means the positive half line, it has a lot of order preserving bijections which are not additive, sure. So without this homogeneity, in that generality, we don't have this result. Surely we don't have this result. We can omit this homogeneity. There are results, very nice results by Mori, that in von Neumann algebras without commutative direct summands, that can be dropped, that condition. But unfortunately, this works only for von Neumann algebras, and as we will see, we need such a result for C-star algebras. Okay, and then maybe I skip this. It's not so. How much time do I have? Okay, just a few words about this. So you remember that we had the structure of Jordan triple isomorphisms in the setting of von Neumann algebras. And this, at least for von Neumann factors. And this gives the possibility to generalize our result on Thomson isometries for a much larger collection of not necessarily metrics, but so-called divergences or generalized distance measures. what is that? So you remember the formula of the Thomson metric, and we just changed logarithm here to an arbitrary function with the condition that it's continuous and there is only one constraint, namely it takes the value 0 only at 1, like the logarithm. And we can also change the norm, the C star norm, to a quite arbitrary norm on A. And what we obtain, this is no longer a metric, but it has this definiteness property. We call such a function a generalized distance measure. And such generalized distance measures appear in applications. Several of them play important roles, for example, in optimization, defined on matrix algebras. For example, Stein loss, symmetric Stein divergence, Jeffreys-Kuhlbach-Leibler divergence, and so on. In all those cases, the norm is the trace norm, and the function the functions are those ones. So not the logarithm, but other functions having that property what I mentioned. And using our former result concerning Jordan triple isomorphisms in the setting of von Neumann algebras, we can determine the corresponding symmetries, that is maps preserving those generalized distance measures. Okay, and now we go to another metric, and it's isometries. Beer's metric. The Beer's metric is a very important distance in quantum information science. And it is also called Beer's Wasserstein metric because it has connections to optimal transport as well. And recently, Ferencz and his co-authors generalized this concept, originally defined for matrices, for the general setting of C-star algebras. C-star algebras that carry faithful traces. So a trace on a C-star algebra is a positive linear tracial functional, and we call it faithful if it has this property. So the trace of a positive element implies that this element is necessarily 0. And then the definition of the Beer's metric is as follows, where this quantity is the so-called fidelity of A and B, and then you have this, and one can show it's not easy to see. In the case of matrices, there is a trick, a quite nice trick, how to see that this is a metric. But in the setting of C-star algebras, this is quite hard work to prove. It was done by Ferencz to show that this is a metric on the positive definite and also the positive semi-definite code. Okay, and what about their the corresponding isometries? Ferencz obtained results on the isometries, but he considered so-called quantum channels, and they are linear maps. So he assumed linearity, and I could describe Beer's isometries without assuming any sort of linearity. Here is the result. If we have C-star algebras with faithful traces, and we have a map, a surjective map, then it is a Beer's isometry, Beer's Wasserstein isometry, if and only if, once again, we have the precise structure, again, a Jordan star isomorphism, a two-sided multiplication, but in this case, this element is necessarily a central element in B. So actually, it's a one-sided multiplication plus a certain trace preserving property. What about the proof? The proof uses heavily our, let me call, big corollary. How? We will characterize the order using the Beer's metric. And here is the characterization. If we consider this set of numbers, then this set is bounded from above if and only if A is less than or equal to B. This can be proved. So using the Beer's metric, we have a characterization of the order. And because phi preserves the Beer's metric, then it preserves the order. That's the main point. And then we can also see that phi preserves the fidelity. Then using that, phi is necessarily preserves scalar multiple. So it's positive homogeneous. And our corollary applies. Of course, there are several things to do. How one can get that C is central. This comes from the trace preserving property. So the proof is not as short as it appears here. It's much longer, but those are the main steps in the proof. Now I arrive to the last part of my talk. Preservers of the norm of means. So we had mean preservers. We had also kinds of metric preserving transformations. And what about preservers of the norm of means? Why to consider them? The motivation comes from two directions. The first one is the former study of norm additive maps. They were norm additive maps which preserve the norm of the sum. And such maps were first studied on function algebras. So as maps, as operators on function algebras by Thomas Tonev and his group. Their aim was to present conditions for nonlinear maps to guarantee that they are weighted composition operators. And it's obvious that the norm additivity property it's equivalent to the preservation of the norm of the arithmetic mean, because you just divide by 2. That's all. So this gives some motivation. If we have something for the arithmetic mean, let's try to discuss the problem in the setting of more general means. And the other motivation comes from the following. Recently, we investigated certain quantum symmetries, namely studied maps on so-called density spaces of C-star algebras, which preserve different sources of quantum Rényi relative entropies. Those are very important concepts in quantum information science, and they are more or less traces of certain variants of the geometric mean. So trace norms, so norms of variants of the geometric mean, so norms of means, geometric means. So we consider the problem of norm preservers on preservers of the norm of means in the setting of general C-star algebras. What is the first question? Of course, the arithmetic mean or norm additive maps on C-star algebras between positive definite counts. And the result looks very simple. A bijective map satisfies this equality, if and only if it extends to Jordan star isomorphism. Of course, every Jordan star isomorphism has this property, its triviality, but the other direction is very complicated. So the result is very compact, looks very simple, but the proof is rather complicated and surprisingly difficult. Once again, the main point is somehow to use our big corollary. This is a joint result with Dong, Li, and Wong. And prior to that, we described the preservers of the norm of the geometric mean with Chavabi and Bekta, and obtained the same. Why we studied this question? Because this is the closest one to the Rényi relative entropies, because as I mentioned, Rényi relative entropies are more or less traces of geometric, the trace of the geometric mean. but in a general C-star algebra, we don't have trace, so we consider the norm instead of the trace. And the conclusion is the same. Those maps are exactly the functions, the transformations, which can be extended to Jordan star isomorphisms between the underlying algebras. And finally, the third fundamental mean is the harmonic mean, and we have the same conclusion, but we do not know we don't have the result for general C-star algebras, only for AW star algebras, which are rather close to von Neumann algebras. They are more general than von Neumann algebras, but rather close to them. Okay, how to prove those statements? Again, the strategy is to prove that the maps in question are necessarily positive homogeneous order isomorphisms, and then apply our result on the structure of such maps. I mean, the big corollary. So the first thing, but this is only the first thing, characterization of the order. Because we also need characterization, and we also need to prove that the maps are positive homogeneous, and this is very difficult in the case of quite difficult in the case of the arithmetic mean, for example. So we need to characterize the order using the norm of the norm of the corresponding means. Here are the characterizations. They are of the same kind, and as for the arithmetic mean and the harmonic mean, those are just very simple. I mean, those are simple things. As for the geometric mean, this is quite complicated to prove that the order can be characterized in such a manner. And I think it's time to finish my talk. I just want to say that because of that, and because of this characterization played such an important role in the description of those maps, what I've been speaking about. So recently I'm considering this problem independently, namely study the question which Kubo-Ondo means. I mean, the norms of Kubo-Ondo means characterize the order. So for which means, maybe symmetric Kubo-Ondo means, such a characterization is true. And I have some results, but I'm very far from being the final, to have the final picture. This is an interesting question with several really non-trivial problems. And as the last sentence, last words, here we were speaking about Kubo-Ondo means, but there are plenty of other means. That's true that Kubo-Ondo means they form a collection of means. So this is a large family of means, but there are other type of means, important means. For example, Fiedler-like spectral geometric mean, Wasserstein mean, and as for power means, the conventional power means, and some of the problems similar to the ones what we discussed here I find really exciting and challenging. So there are a lot of things one can do here. For example, as for the isomorphisms of the Fiedler-like spectral geometric mean, I do not have a result even for matrix algebras. Okay, so that's all, and here are the references. That's the paper on quantum ring relative entropies, which gave me the motivation to study norm of mean preservers, and a recent paper on preservers as the Wasserstein mean. And that's all. Thank you so much for your kind attention.
Thank you indeed. Let's thank Lajos first. Questions or comments for Lajos? I have a general question, and maybe it's not an honest question to ask, but anyhow, please allow me. In all of these means, I mean, is this foreseeable to consider a general metric and develop a theory without, I mean, specifying to a very, I mean, like arithmetic mean or geometric mean? I mean, a general theory which applies to all of them equally. Is it possible? Can we have such a hope?
So we don't have such a, so we have this Kubo domain. This is a very compact theory, okay? For example, this Fiedler-Tag mean is not a Kubo domain. So I don't have such a theory which would include all Kubo means and all those means that I mentioned. For example, the conventional power mean and the Wasserstein mean and the Fiedler-Tag geometric mean. No, I don't know about that. And I'm rather skeptical to have such a...
Absolutely. As I said, my question is not an honest question, but
No. That's a natural question, but I think that it's not possible to have.
It's a very big hope to have.
Yeah.
Because even as you mentioned in your talk, even in those special cases, we use the word special case, but still the proofs are very complicated.
Yes. Surprisingly.
Yeah. Any further comment or questions? If not, let's thank Lajos again.
Thank you so much. Thank you.
Thank you indeed.